So I want to do an example of a polar curve, so I'm going to look at r equals 3 sine 2 theta. If you do the graph of this, it looks like this. That's called a four-petal rose. It's an interesting, if you look at the way it traces out, it actually traces out this way, and then it goes into this lower quadrant. It's going to affect things, and then into quadrant 3, and then it traces out into quadrant 4 or to quadrant 2. All right. Also, I played around with it. You can see a complete graph from 0 to 2 pi, but you can't shorten that. Now we're going to be doing calculus on this thing, so we are going to need the r derivative with respect to theta, and so you can just compute that real quick. It's 6 cosine 2 theta. All right, so here's what the three things we're going to do. We're going to find the slope of the tangent line when theta is pi over 3. We're going to find the polar coordinates of all the horizontal tangents and find the polar coordinates of the vertical tangents. All right, so we get started on part A. So we're going to need the slope. That's dy dx, and just like with parametric equations, that would be dy d theta over dx d theta. So this is a general formula you get by going through the product rule with polar coordinates for the slope of a tangent line. Alright, so we just need to plug things in now. We've already computed r prime and we know what r is, so we just fill things into that expression and we get this complicated looking expression. Now, the key thing is here, we have some mixing of angles. We have twice angles and single angles. And so we can apply the double angle identities to these parts right here. So there's the double angle identities that we'll use. And fill those in for those 2 theta parts. So I go and fill that stuff out, and I end up, this looks very complicated, but just take it a step at a time. One thing to notice is there's a 6 in each part here, so we can factor those out and cancel. So I'm going to save a line and not show that, but the 6's go away. And then, once the 6's are gone, you just look at it carefully. Notice in the top, here's our main add right here. There's a sine theta here and a sine theta here. So I can factor that out front. Same thing in the denominator, except I have a cosine and a cosine, so I can factor out a cosine. So you just got to look carefully here. If I take the sine out here, I have cosine squared minus sine squared. And then if I take the sine out here, I have cosine squared. Same thing in the denominator. Once I factor out that cosine of theta, I have cosine squared minus sine squared there, and then this cosine's gone, so I got sine squared right there. All right, now you can just combine those the multiplicative parts and say in the top you have 2 cosine squared theta, in the bottom you have minus 2 sine squared theta. So there's a pretty simplified expression for our slope. All right, and that's what we're going to use. Alright, so part A says to find the slope when theta is pi over 3. So theta pi over 3, I fill pi over 3 into all this. Then you just either need to look up or know your trig values. The cosine of pi over 3 is a half. Sine of pi over 3 is square root 3 over 2. Square each one of those. You get 1/4 and 3/4. Like that. So I'm just filling all that stuff into this expression. So you end up with this. You subtract your fractions, you get negative 1/4 and negative 5/4. And then notice my numerator is the negative square root of 3 over 8. And then I'm dividing by negative 5 over 8, so I inverted and multiplied. Go through, do your simplifying. You end up with the slope as the square root of 3 over 5. Alright, and you can check that with your calculator, it checks out. Alright, so then on part B, we're doing the horizontal tangents. Remember, this is our slope, so you have a horizontal tangent if that slope is 0. We have a fractional expression. The only way a fraction equals 0 is if the numerator is equal to 0. So I set the numerator equal to 0. Alright, this is factored, so I can set either sine theta equal to 0 or this expression right here equal to 0. And just remember, we're looking for solutions in 0 to 2 pi. Alright, sine of theta equals 0 is pretty straightforward. That occurs when theta is 0 and pi. Alright, and now we got to set this thing equal to 0. The problem is we have 2 trig functions. We could do this in terms of tangent, but it's typically easier just to get it in terms of sine and cosine. So I'm going to take that cosine squared and rewrite it as 1 minus sine squared. Multiply things out, you end up with 2 minus 3 sine squared of theta is equal to 0. Go and isolate your sine squared. you end up with 2/3. Now just remember we got to take the square root, but whenever we take the square root we need that plus or minus in front. So you get the sine of theta is plus or minus square root of 2/3. Alright, so thinking in terms of reference angles and quadrants, the reference angle is the inverse sine of square root of 2/3. With that, usually we have to think about the quadrants, but since we have this plus and minus, that means we're going to get a solution in every quadrant. Quadrants 1, 2, and 3, and 4. So here's our quadrant 1 solution, here's our quadrant 2 solution, here's our quadrant 3 solution, and here's our quadrant 4 solution. So we get those four strange looking angles. Don't worry too much about them. Now, so that's telling us where the horizontal tangents occur at. All right. Now, but the problem said to find the polar coordinates for them. So these are the theta values. We need the r values. All right. And just remember r is 3 sine of 2 theta. So basically you're just plugging them in. Now for 0 and pi it's pretty straightforward. You're plugging in 0 for theta. You end up with the sine of 0, which is 0. And same thing at pi, you end up with the sine of 2 pi. Sine of 2 pi is also 0. So those two are pretty straightforward. Remember the general format is r theta whenever you're doing polar coordinates. For some reason the coordinates are reversed around. Alright, so we get those two. Now the thing is we've got to plug these in. Alright, so if you want, just plug them in for r. Okay, so whenever you plug those angles in for r, here's your angle, the inverse sine of square root of 2/3, and then pi minus the inverse sine of square root of 2/3, etc. These are your angles, so r theta. Now, and then remember we had these two that we found on the previous page. So you could write them that way. You folks that are more interested in trig or more adept at trig, you can actually simplify these things out. And those radiuses end up either being plus or minus 2 square root of 2. So you just got to know a bit more trig to get them simplified out that way. Alright, now we're ready for the vertical tangents. So now we're going to set our denominator equal to 0. And again, this is factored, so I can set cosine equal to 0, cosine equals 0 at pi over 2 and 3 pi over 2. And then just like last problem, last part, we set this quadratic part equal to 0. I wrote the cosine squared as 1 minus sine squared. You could have just as easily written this as 1 minus cosine squared. So we get something that looks pretty different, except now we have a 1 and a 3. So you end up with sine squared of theta is equal to 1/3. And take your square root. You just got to remember you need that plus or minus. So just like with last problem, that means we get our reference angle, but that plus or minus tells me I have a solution in every quadrant. So there's my angles. So now you just need to plug those thetas into your r equation. Just when theta is equal to pi over 2, let's come back here, we're going to have pi over 2. The 2's are going to cancel, so you're going to have the sine of pi. You're going to get 0 again. Same thing at 3 pi over 2. So the radius is 0 at these two basic solutions up here. Alright, and then again, if you want, it just gives you very complicated expressions, but if you want for the polar coordinates for these strange angles, you can plug those in. Interestingly enough, you do get those same radiuses just at different angles. It's pretty interesting what goes on with those vertical and horizontal tangents, especially at the origin. So if you remember, the graph goes like this. Oops, sorry, I didn't draw that part very well, but what's strange is these basic solutions right here, they're all occurring at the origin, just at different angles. So you actually have two verticals whenever it passes through certain points, and then you also have two horizontals at those certain points. So it's a strange kind of behavior, but that's the way it happens. Alright, I hope that helps.